Hey everybody, Mr. Piercy here. This is going to be the second part of our lesson on reasoning in algebra and geometry. So in the last video, we kind of talked about a little bit about what a proof was, and that there are statements that we use and reasons for those statements in order to justify the a conclusion in deductive reasoning, or using deductive reasoning. Now there are three basic proofs that we use in geometry. The first, and probably the most obvious, is what we would refer to as a paragraph proof. The reason why I would say it's kind of the obvious one is because if you had to justify something to someone, regardless of what it is, whether it's a math thing or a non-math thing, uh, we use it using language. And if we use language to justify something, we can obviously write it down in the form of a paragraph. So that's what a paragraph proof is. Now they can get a little complicated depending on what the type of proof is and maybe the math associated with it, but it is kind of the most intuitive way of proving something. So the second one is a flowchart proof. Now a flowchart proof looks a lot like maybe the way a system is organized. It could be a computer programming language. It could be even like the organization of a business. But this on the left here, the image, this is what a flowchart proof looks like, where the statements are in a bubble or a box of some kind, and the reasons are given outside of the box. It could be written underneath it, it could be written above it. Generally, you might want to kind of write it underneath the because the statements or the reasons for a statement generally are a little bit more involved or a little bit more lengthy. So you can see writing something underneath, writing the reason underneath the statement would be a little bit easier to see. And the last one is a two-column proof. Two-column proof. And they're called that because it looks like two columns. It's like a T-chart here. So here's my two-column proof. Now, out of the three proofs that we see here, probably, let me go ahead and just reason. Out of the three proofs that we have, the two that we're probably going to see the most of are going to be paragraph proofs and two-column proofs. Now, paragraph proofs, again, that's just something that if you were explaining something to somebody verbally, if you just wrote down what you said, there's a paragraph proof. Well, out of the two-column proof and the flowchart proof, the one that generally seems to get used the most is a two-column proof. Now, really the organization, or really there's no difference between what a two-column proof is and what a flowchart proof is, other than the way that we organize the information. Here in a two-column proof, instead of putting the statements in a bubble and using the statements to, point to a new kind of conclusion, well, it just kind of flows from top to bottom. Well, we have this, we have this, we have this, therefore this is our conclusion. So that's what a two-column proof and a flowchart proof and a paragraph proof, that's kind of what they are. Here's our textbook's definition of what a proof is, what it looks like, and so on. Now, the one thing that I really do want to point out here is almost always you're going to be given some information, whether it's in a statement like this or it's just in a diagram. And that given information is pretty much, I won't say 100% because I have seen it otherwise, but about 99.9% of the time, whatever is given to you is what we start with when we start writing our proof. That's like the first statement and reason that we have. Now, let me pick another color here. Now, what you're trying to prove, that is pretty much always going to be your very last statement in your proof. And this is one of the things that I struggle with every year with students is that uh, a lot of times I'll see students try to use the statement that they're trying to prove as something else in the proof. Okay? If I'm trying to prove a statement, it needs to be the last thing that I say. So I can say this statement and with my final reason and conclude the proof. So when you're writing a two-column proof, keep that in mind. The given information is pretty much always going to be the very first thing that you do, and the statement that you're proving is going to be the last thing that you do. So everything else in between that we fill in the blanks with, well, that's just going to be, those are our kind of the chain of statements that we're going to be making to go from point A to point B. So keep that in mind when you're writing a proof. Now these examples that I'm providing here, they're not specific to math or geometry at all. While we probably don't use two-column proofs outside of math, they do have applications outside of it. So here are a couple of examples. The one on the left I actually just found on the internet and said, hey, that's not a bad way of writing a proof. So what we're trying to prove is why Lisa was on time. And so the final reason was because the donut arrived before Henry did. Okay, so there's a chain of events that are taking place. Now the one on the right is one I actually kind of made up myself, where it says here we have a statement that that's given to me that dogs are domesticated animals that people keep as pets. Now what I'm trying to prove is that dogs are man's best friend, because obviously I'm biased. I'm a big time dog lover. But so here's maybe like the 0.1% of the time where I'm not actually starting my proof with my given statement that dogs are domesticated animals. I'm just giving statements and reasons to prove, to justify the final statement that dogs are man's best friend. So, just read read it if you want to. I think it's really neat. You may agree, you may disagree, but that's okay. This was my two-column proof of why dogs are man's best friend, because, well, they are. I mean, when was the last time you didn't see a dog and want to pet it and say, "Ooh, doggy, doggy, yay!" Go fetch a stick and play with it. So now we're going to move on to an actual two-column proof for how it's used in geometry. Now, we're given our initial statement, so that really should be the very first thing that we have in our proof. So they're given to me the information that the measure of angle 1 is equal to the measure of angle 3. And the reason for that, the reason I can make that statement is because that's given information. So that's all the reason I need to provide. Well, it was given to me. That's why I can say it. So going on to the next statement. The next statement that we have is that the measurement of angle 1, the measurement of angle 2 has to be equal to the measurement of angle 2. Now, if you refer back in your notes to that sheet or to the table that has all of the, a lot of the general reasons for why we're saying stuff, well, if I say something is equal to itself, the reason why I say that is because of the reflexive property of equality, which kind of makes sense. You can see a little bit of overlapping things here. So in the diagram, there's several angles that we could name. I could name the overall angle AED. I could name a smaller angle AEB, but I could also name a smaller angle AEC that contains angle 2, and another smaller angle BED that also contains angle 2. So because that angle could be shared between more than one angle, well, it has to, because it's the same angle in more than one angle, the same measurement, that has to be the same. So that's the reflexive property of equality. So now we're going to be saying, well, because angle 2 is shared between more than one angle, I can say that the measurement of angle 1 plus the measurement of angle 2 should be equal to the measurement of angle 2 plus the measurement of angle 3. Well, that kind of makes sense because we've already established that 1 and 3 are the same. That was given to me. And if angle 2 doesn't change, then 1 plus 2 should be the same as 3 plus 2. So the reason that we can say that, well, that's simply the addition property of equality. Now I know we're not necessarily moving something across an equal sign like we did in an algebraic step, but here we're using in a geometry from a geometry mindset, so that's why we're going to use it here. Now, moving on to statement number 4. Well, the measurement of angle 1 and the measurement of angle 2 make up the overall angle measurement for angle AEC. So angle 3 and angle 2, and those are added together, that equals the overall measurement of angle DEB. So in that statement, we're taking two smaller parts and making one bigger angle. So that isn't actually on your reasons in this handout. That's going back to something even earlier called the angle addition postulate. This simply says if I take smaller angles and combine them, I get a bigger angle. So now that we've established that angle 1 plus angle 2 is this, and angle 3 plus angle 2 is this, now, because we've already established earlier in our proof that angle 1 and 3 are the same, and angle 2 is obviously the same, and that these angles add together to make these other angles, well, that allows me to make the conclusion, or to get to my proof, which is my final statement. Let me go ahead and pick another color here, where I'm saying, okay, so the statement that I'm trying to prove, and again, that should really be the last statement in my proof. Well, what's the reason for that? Well, really, I'm just substituting the fact that we've proven these angles are the same, and that the sums of these other angles are the same. Well, then I'm substituting the values for those angles to show that, yes, this is the reason why that statement saying the measurement of angle AEC and the measurement of angle DEB are indeed the same. So here we have our final example that we're going to look at. Now, if you notice in this one, I'm missing something. According to what I've seen in the other statements, what was the given information? Well, information that's given to you doesn't have to be written specifically down. Sometimes information can be given to you in the figure itself. And that's exactly what we see with the hash marks. Because the hash marks are provided for you, you don't have to be told that A, B, and C, D are going to be the same. That is something that we can take from the information or from the diagram itself. And so there's my given information. Even though they didn't write it out for me, they said, well, in the diagram, we can see, based on what we know about how geometry is, symbolized, that those two segments have to be the same. So there's my given information. Well, what can I make beyond that? Well, if they are congruent, they must also be equal to each other. Now here, this reason isn't something that came from our table. It's just kind of a common sense thing. Congruent segments have to be equal because they're the same length. That's what makes them congruent in the first place. So what else can we kind of reason out? Well, in between here, very similar to what we saw in the angle diagram a second ago, we do have a segment labeled BC that could kind of overlap between angle AC and angle BD. Well, if that segment can be shared between more than one segment, then it must be the same measurement in either of the other segments that it uses, or that uses it, I should say. So I can say that BC must always be equal to BC because anything that uses that same thing, it has to be equal in those things. So there's the reflexive property of equality. Okay, well, what segments actually use it? So, because what we're trying to show is that segment AC is actually congruent to segment BD. Well, what makes up those parts? Well, if AB and CD are the same length, and BC is always the same, then that means whatever AB is plus BC has to be the same as BC plus CD. And that's just the addition property of equality again, showing itself in a geometry situation. Well, moving on, we can now say very similar to what we did with the angles. I can say that the two smaller parts, AB and BC, make the bigger segment that I'm trying to show. Remember, oops, I didn't mean to do that. No, don't do that. Let's go back. Let me go back to my pen. What we're trying to do is we're trying to show that this and this are congruent because that's the statement that we're trying to prove. So the two smaller parts that make the part that I'm trying to prove of one segment and the two smaller parts that make the other segment that I'm trying to work for in my proof, well, that's just going back again to our segment addition postulate. That's old stuff. It's not going to show up in our new statements or in our new reasons. That's old material that we already have to kind of be aware of. So if we can say that the two smaller parts that make AC and the two smaller parts that make BD have already been the same, then we must be able to conclude that AC has to be congruent to BD because of the substitution property. Well, the final statement that we're actually trying to prove is not about the substitution property of equality. We're trying to show that something is congruent to something else. So the final statement is, again, what we were trying to prove, but the reason, again, isn't so much a purely geometry or purely algebraic reason. It's just a little bit of common sense. Well, segments that have equal length must be congruent. So we started off by saying that these smaller parts were the same. Well, this part in the middle that's shared is also the same. So the sum of the two small parts that make the bigger ones that we're trying to show are the same. Well, we could just substitute those numbers into whatever they wound up being. And therefore, the two segments, AC and BD, have to be equal to each other. And obviously, if they're equal, they have to be congruent because, well, that's just common sense. So these are examples of the kinds of things that we're going to be practicing in geometry using a two-column proof. Now, this is just the introduction. We're going to be seeing more two-column proofs later on down the road. We're going to be doing a fair amount of two-column proofs when we do certain things with triangles. But this is the introduction. I just wanted to give you the framework of how they are used, what do they look like, and some overall, basic practice of how we're going to be doing these things. So if you have questions about anything that you've seen in either of the two videos that present reasoning in algebra and geometry, please be sure to let me know in either an email in the comment section of the Google Classroom, or just talk to each other in your individual classes, because I know some of you are actually sitting together at the same time. But until then, ladies and gentlemen, I will look forward to any comments and or questions that you have. And until the next video, until the next lesson, guys, thanks for watching. Take care and talk to you soon.